this presentation, I'm going to introduce a specific ETP problem, which this problem is really common, happens in Japan. And I'm going to use the genetic algorithm to solve this specific special problem. And my presentation can be simply divided into 4 parts. So first about the proposed problem, then the detail of my algorithm, the testing, and finally the conclusion and my further research plan. So first part about the proposed problem, okay? So as I said, this is a special ETP problem in Japanese university. So commonly in Japan, university or college, a final year student has to give a presentation in order to evaluate their research. But the problem is, all the special things in Japan, people are, they like to call all the students from the same laboratory, from the same supervisor. They call them a session, okay? And they want to all the students from the same session with the same supervisor hold the presentation together. Okay, so what together means is the presentation be held one after another and in the same room and be held in the same day. And moreover, a student normally have 3 examiners, and one of them should be the supervisor. The other 2 is what they call deputy examiner, who is familiar with the student's topic. And all these 3 examiners are decided at the very beginning and which cannot be changed. So this is this several constraint is what we call hard constraint in our project. And the problem is, as we can see, because of there's a concept called a session. Okay, so this session cannot be broken and should be held in one day. So the traditional J operation does no longer work because the random crossover operation will break the session and in a high probability, and therefore generate a huge number of the unfitable solution. So therefore, that's why we want to design a new genetic algorithm approach to solve these special cases. And our project actually using the Excel VBA program language, which can allow the university staff use this program easily. So beside of the hard constraint, what I said before, this problem also contains several soft constraints, which listed here. You can see the first 1 and 2 means we want to allocate the examiner to their available places. And the third one and fourth one means we want to allocate the examiner in contiguous, okay, in the contiguous time slot in order to save the examiner or the professor's time. And of course, an examiner cannot be occurs in 2 places at the same time. Okay, the 6th one means we want to allocate the presentation start from the first period of the each day, each room as possible as we can. So depending on the priority of this constraint, for each constraint, we will be giving a penalty point. And so then this problem is then become to an optimization problem, which we want to find a solution with the smallest or minimest penalty point. Okay, so we want to use a genetic algorithm to optimize this one. And next page, this page shows an example of the students list. So in this example, as we said, each student, as we can see here, each student has 3 examiners, and here we totally have 1, 2, 3, 4, 5 prime examiner, which will be the student supervisor. So in this example, we can say that we have 5 sessions. Okay. And then the exam schedule here shows so this schedule we can check when do our professor have the time to attend the presentation. So we have basically 3 levels of the priority across here. You can see in the schedule means the examiner do not have the time for this moment. A triangle means the examiner has the time but personally they don't want to attend the presentation. Okay, And space means the examiner is available for this moment. And then about the chromosome representation. In this algorithm, we use the direct chromosome representation. For example, here shows a 2 days presentation schedule. And we can see we have 2 days here. For each day, we have 2 rooms. And for each room, we have a maximum 10 time slot. So this means this room can hold a maximum 10 presentation. Okay, so and our chromosome will be a number string with the length of 2 days times 2 room times 10 presentation. So in total 40 length of the number string. So in this number string, each non-zero number corresponds to a specific student, and 0 means for this time slot there is no student to hold the presentation. Okay, so that's all for the introduction about the problem. Now let's see the second part, the proposed algorithm. Here is a simple flowchart for my algorithm. So basically you can see this is the basic GA, but here we have some special improvement, what we call pre-training, which I will introduce in detail later on. So first, let's say about the initialization. Okay, so we design a specific special initialization operation for this problem. So okay, so to generate the initial population, first what we should do is we have the student list here. We have to reorder all the sessions from here. You can see the session 1, 2, 3, 4. We reorder them, and also we have to reorder all the students inside of the one session. So for example, here we have 1, 2, 3, 4 in this session, but here we have 3, 4, 1, 2. Okay, so we disorder them. And then secondly, we have this empty schedule. We have to allocate all the students to this schedule. Okay, so first, the first session here, you can see the first session here. We have to allocate this session to the first available place of the first room in the first day. Okay, then the second session will be allocated to the first available place of the second room in the first day, and similarly so on. So then once all the first position of each room has been allocated with the session, then the remaining session will be randomly allocated to a random available place. So for example, with the randomly available here, then we allocate them to here. And then we can, based on this schedule, we can generate the initial population chromosome. So this initialization approach has 3 advantages or pros. First, the hard constraint can be satisfied. What we mean is a whole session cannot be broken and every single session should be healed in the same day. This initialization approach can satisfy this. Secondly, this initialization way can keep certain level of the randomness. And finally, based on our experience during the design of the schedule in the real world, people usually want to make an event start from the first time slot of a day isn't. So this kind of design can satisfy this requirement. And in order to reduce some convergence time in the main calculation of the JA. And then about the fitness evaluation, we have mentioned before in the proposed problem, we use the penalty point system. Okay, so if a solution, okay, against any constraint, a penalty will be given. Then we want to find a solution with the smallest penalty point. So that's the fitness evaluation. Then let's introduce about the selection and the mutation part. For the selection in this JA, the tournament selection has to be used. Okay, so in specific, for each time, 2 random individuals will be selected, and the one with the larger fitness value will be remained to the next generation. And the mutation. So the mutation approach in this algorithm can be divided into two steps. In step one, we will randomly select two students from a random session. For example, here we have student 8 and 10, then we swap their position. So this is the first step of the mutation. In the step two of the mutation, we will randomly select another session. Okay, so this session will be randomly moved up or down to a available position. Okay, so like this, we have position in green color here. We randomly move up or down. Okay, so in this example, we move this session to here. Well, then let's introduce the crossover part, which is the main part of this algorithm. So during the crossover, because we have to make sure that a whole session will not be broken. And meanwhile, we have to make sure that a whole session has to be healed or to be placed in the single day. Therefore, the normal or traditional crossover does no longer work. Therefore, we designed this specific special crossover operator, what we call the constraint-based crossover. So in this crossover, in the first step, two parent chromosomes here like this will be selected, and then two random sessions will be selected from each of the chromosomes. So these two sessions could be either a real session or a zero session. So a zero session means no student is placed in this time slot. Okay, so then I'm going to give two examples to introduce this special crossover operation. So in this first example, we select two real sessions. Okay, so in this example here, we have two chromosomes. We select session, this one from student 8 to 11, another one from student 12 to 40. And similarly here, we have to select the same session like this. We give their different color. So session A and B in yellow, session A in yellow, blue, session B in green and red for each chromosome. Then we swap their position. Okay, so this session we moved to here, and this session we moved to here. And the blue section moved to the position of the red, and the red section moved to the position of the blue, like this. So by this way, we complicated the crossover of two chromosomes under the two sessions condition. And we have another example. So one real session select with a zero session. So if we want to select a real session with a zero session, first we have to select a real session. Okay, so we select the session from 8 to 11. And then to select the zero session, first we will randomly point a zero position. So in this example, we randomly point zero position here. You can see here and here. And then we want to try to make a zero session with a student of 4, because the real session would be selected has 4 students. But here you should be realized there is some problem. Okay, so if you look at the red position here, red color here, there is only 2 available spaces, which is not enough for a 4 student session to do the crossover. So in these cases, what we do first, we will try to move the adjacent session, which is the session with student 1 to 4, up or down in order to vacate some spaces. But you see, even we move this session up for one position, there is still not enough spaces. So in these cases, what we do next is we will move, where's my mouse? Okay, so we will move this whole section, this whole adjacent section to another random position, random available position in order to vacate the spaces for the red zero position. Okay, so we move this whole section to here, So therefore, this zero section will have enough spaces to do the crossover. And then therefore the yellow section will move to here, we move the blue zero section to here, the green section will move to here, the red section move to here. So by this way, we will complicate the crossover operation. So up to now, we have already built a basic genetic algorithm for the ETP problem. But during the research, we found that this algorithm does not work well. It usually output a result with a really high penalty. So if we go back to the previous table, we have this constraint table here. You have already been mentioned that because based on the priority, each constraint has different penalty points. The constraint 1, 2, and 5 have relatively larger penalty point, which is the red color here. And the constraint in the green color, 3 and 4, has relatively smaller penalty point. This causes a problem because the constraint with larger penalty points will have a higher probability or higher ability to control the direction of the evolution. In another word, we will lose the evolution information about the constraint with smaller penalty points, which means the constraint with smaller penalty will be ignored during the calculation. To solve this problem, before the mean iteration of the JA calculation, we add an improvement, which is called pretraining. Okay, so in specific, before the mean calculation, 3 iterations of the pretraining is added. During the pretraining, the individual or the chromosome are only being evaluated by part of the constraint, by the constraint with the smaller penalty point, which is the constraint 3 and 4. Okay, so by this way, some good solution about the constraint 3 and 4 will be generated in advance before the mean calculation. So therefore, the parameter convergence can be avoided in a way because we have already generated some partial good solution first. So up to now, we complicated the whole algorithm. Then the test part. So first test is a real application example. So by using this proposed algorithm, we successfully completed the schedule arrangement for the master graduation presentation in the informatics or the green science school in the Sophia University. The data has around 40 to 50 students and has in total 15 sessions and around 22 to 25 examiners. And the results are used in real situations successfully. And then test 2 is about what we do a comparison between the proposed J with the pre-training and the model without the pre-training. Okay, so the proposed J with pre-training is in the blue color and the without the pre-training is in the orange color. So if you look at this table, you can find that the ID of the pre-training, can reduce the penalty points. In another word, improves the result quality a lot. And meanwhile, the calculation speed is maintained at the same level. Okay, so that's all. So let's do a conclusion. So in this presentation, we proposed a novel or new genetic algorithm approach to solve a special ETP, which commonly happens in Japanese university. And this module is implemented as an Excel VBA program, which can allow the university staff to use it easily. And the proposed algorithm has been used in real situations successfully, and we giving an improvement called pre-training, and the pre-training shows an apparent improvement on the result quality for the proposed model. About the further idea and the research, the first one is we want to apply the mimetic structure, which combines the local search algorithm and GE together in order to improve the result quality. And secondly, we want to apply the island model to the genetic algorithm in order to improve the diversity of the population and therefore improve the result quality as well. And finally, we want to design a better crossover operator for these special cases of the ATP. Okay, so that's all for my presentation. Thank you.